In this video, I'd like to take a field trip of sorts. We'll take a nature walk through the jungle of Gaussian processes and see what all the different species of Gaussian processes look like and all the different fantastic forms that they can take. So our first specimen will be this simplest non-trivial example of random lines that we drew. And so I have all set up here in MATLAB. I have a script which actually, if you were to study this, you would see how to implement sampling from a Gaussian process. And it's very simple. It's just exactly the code that you see on the page here. That's it. It's very simple, and most of it is just setup. So most of it is choosing a kernel. We use the word kernel for covariance function also. And then, choosing which points we're going to sample it at. And then we construct the covariance matrix for those points. And then this is the sampling here. This is really the only thing that's going on in sampling from a Gaussian process is this little hunk of code right here. And then we plot it. So I'm just going to, you can study this on your own if you want, but I'm just going to run this for some different kernels and we'll see what we get. So the first one is this linear kernel that just is going to give us lines. So this is in the case when x and y are just points in R, they're just real numbers. This is our kernel. And so let's run it. I ran it once here and we get a line and it looked sort of like what we drew. It goes through 0. And let's run it a few times and we'll get a few more. I'm only showing it from 0 to 1 here on the x-axis. But it would of course keep going on in the other direction, the minus infinity. And so we get all these lines. And it looks just like what we drew. So that's our first specimen, and maybe I'll mention that we can generalize this special case here. We can actually write down what the covariance function is. I'll just go ahead and, without deriving it, I'll just write down what the covariance function is for that little example. So our first little example is, we'll generalize it to random planes, and maybe I'll show you the picture for random planes in higher dimensions. So for random planes, our set S is RD. You can always think of D as 1 for our simple example. The mean function is 0 for all x. I'm going to use x instead of t or s here. And the covariance function is x transpose y. So when D is 1, this just reduces to x times y. And you can check that, in fact, that simple example of random lines has that mean and covariance function. Pretty much all the mean functions we're going to use are going to be mean 0. And let me also show you, so since I defined for random planes, I have this other script which draws samples from two-dimensional Gaussian processes, which are sometimes called Gaussian random fields. And you can study this one also if you so choose. And so so here I have this, I called it the linear kernel, and I just have a 1 here so I can change the scale. And let's run this and see what we get. It takes a little longer because it's a larger matrix that we're working with. So we get this is a sample. This is a draw from that Gaussian process. So each point in the plane here, before we had just R, but now each point in the plane, this is like the x1 y x1 x2 plane or xy plane, and then the vertical axis is zx. So let's think about it as x1 x2, and then the vertical axis is zx. So the vertical here is the random thing. And note that this goes through, you can sort of see, it goes through 0, 0, just like in the 1D case. Let's run it again. Get a different plane. So each one is a random plane. You can see that it's a plane. Run it a few times. And so you can see that each time we just get a different random plane. And each of these is a Gaussian. Well, these are samples from a Gaussian process. Okay, that was our first slight generalization. And now we're going to take a look at something quite a bit more interesting, which is standard Brownian motion. Standard Brownian motion is a very famous Gaussian process, very, very heavily studied, and we'll just look at it in the case of a one-dimensional Gaussian, one-dimensional Brownian motion. This is also called a Wiener process after Norbert Wiener. And S in this case is going to be the non-negative real numbers, our mean function. Again, I'm going to use t now instead of x because we often think of it as time. And the covariance function is the min of s and t. Seems a bit strange. The min of s and t. And yet, you can prove that, in fact, this is a, well, when we define covariance functions, you can prove that this is, in fact, a valid covariance function. This is our standard Brownian motion, and I have set up in our script over here. Let's go back. I have set up kernel 2 is Brownian motion. So it's the min. I put this constant here. You can change the variance by changing these constants, but we'll just leave it as 1 for now. And let's run that. Oh, I have to clear. Sorry. Clear. Let me add that in the script. Clear. There we go. And so this is a draw. This is a sample from Brownian motion. And now, to be clear, you know, we're only drawing the samples at these points that I've indicated with the dots. And I'm drawing the little lines in between so you can visually sort of see, but maybe just to see a couple without those lines, I'll do it. This is a little bit more accurate representation because the other one was interpolating between. And so each of these is a sample from standard Brownian motion, or at least at these finitely many points. And again, the vertical axis, so on the horizontal axis is our t, and the vertical axis is the random thing, zt. So like z.2 would be this value here. Run that a few times. And each of these is a draw. Oh gosh, what happened? Sorry. Let's go back to our figure, and I wanted to change this over here. There we go. And of course, Brownian motion, as you may know, is often used to model the movement of randomly moving particles, like in physics is used for diffusion processes, and it's also used in many other things as well. Okay, so that's our second specimen, and let's see what else we can find in the jungle here. So what else do we have? Let's see. Oh, and maybe I should mention, for Brownian motion, it's defined by this, and also that it's continuous with probability 1. So just to be clear, that's the definition of Brownian motion, is that it has this mean and covariance, and it's also continuous with probability 1. Okay, a very heavily used Gaussian process in machine learning and for regression uses what's called the squared exponential kernel, or the squared exponential covariance function. And for this, let's look at the 1D case first, maybe. So S is the real numbers. The mean is 0, like we have been taking all along. And the covariance function is e to the minus alpha times the difference between x and y squared. And this is for some alpha positive. Alpha controls sort of, well, you'll see what it controls. Maybe I'll show you actually here. Okay, so this will be kernel number 3. And maybe I'll scooch this over so you can actually see this here. This is our kernel. This one, it's the squared exponential kernel, squared exponential. And I put 100 for that alpha parameter. And this is a little more general because I'm allowing these to be vectors. Okay, so let's run that one. Let's see what we get. So now see, the Brownian motion was all jagged. In fact, Brownian motion is it's nowhere differentiable, if I remember correctly. It's nowhere differentiable with probability 1. And yet this one, when we take this square and the exponent for this, with this exponential kernel, this is in fact smooth. It's very, very smooth, and if I'm not mistaken, it's actually infinitely differentiable with probability 1, perhaps. There must be some caveat like that. Infinitely differentiable, I think. I'm not sure. Maybe I shouldn't say that authoritatively. But at least it looks very smooth. The draws that you get from this Gaussian process. Very beautiful, very smooth, nice curves. So that's the squared exponential. And let's see what else we've got in our well, let's go ahead and generalize this one here. Let's generalize. Maybe I'll just put ... s equals r d mu, so this is all the same. And the covariance function, when we generalize this to rd, you can probably guess, we just take the norm. So I could have just defined that this way the first time. And maybe I'll mention one more here, and then before we get to some more interesting ones. So the Ornstein-Uhlenbeck process. I'm going to run out of time in this video if I want to do all these. Actually, let me stop there for this one, and then we'll continue our nature walk here, looking at all these different weird and wonderful beasts. And I have a couple I think very interesting examples to show you also, sort of the last two that I'm going to show you of these examples. All right, so you'll definitely want to see that.